Hi, I'm Ehsan, a PhD student at the Department of Computer Science, Texas A&M University, and welcome to my presentation for the paper in ICASP 2020. So let's begin. The paper I'm presenting today is Exploring Biobehavioral Signal Trajectories of State Anxiety During Public Speaking. The authors are Ehsanul Haque Nirjhar, which is me, Dr. Amir Behzadan, and Dr. Theodora Chaspari. So let's begin. What is public speaking anxiety? Public speaking anxiety is one of the most common social phobias. I think we all feel it every now and then. It can elicit increased heart rate, voice shaking, or feeling disappointed. So this anxiety has a long-term effect on our academic and professional career. Therefore, it is necessary to design computational models of public speaking so that we can better understand this and potentially design personalized interventions to address it. This detection needs to be personalized and less obtrusive. Public speaking anxiety is often considered momentary or state anxiety, but people who are inherently more stress-prone may suffer more from this. Therefore, personalization requires understanding individual patterns. There are three theoretically grounded patterns of public speaking anxiety. They are sensitization, habituation, and escalation. Habituation means higher anxiety at first, but as time progresses, it dies down. Escalation is the total opposite of it. On the other hand, sensitization refers to low anxiety at first, but as time progresses, it peaks and then comes down. So we need to model these patterns. Previous works in this area have used different biobehavioral feature set to predict self-rated anxiety or audience evaluation, which are good indicators of public speaking anxiety. But there are some issues in these works. First, they rely heavily on self-reported surveys. Next, they use statistical aggregate of biobehavioral measures. This aggregation often loses the temporal patterns mentioned earlier. Therefore, we need something to capture these patterns. In our paper, we address these issues by quantifying temporal patterns of biobehavioral signals to model the time trajectory. We mathematically model the physiological and acoustic features to capture these theoretically grounded time. We propose two models, transient oscillation model and quadratic polynomial model. Next, we show the association of model parameters with individual trait characteristics. And finally, we perform prediction of trait anxiety ratings from these model parameters. In summary, in this paper, first, we performed a field experiment where we collected data from real people. We extracted some features from this data collection process and then did a trajectory modeling. Finally, we checked the association of these model parameters with trait anxiety and estimated this anxiety from the model parameters. We conducted a research experiment with 55 participants. And these participants performed a public speaking task. They were given some common topic to talk about. And after some preparation, they spoke in front of a live audience for 5 minutes. For physiological and acoustic data collection, we used Empatica E4 sensor and microphone. The Empatica E4 watch was used to collect the electrodermal activity and heart rate. Audio signals were collected using the microphone. Apart from these signals, participants completed standardized surveys to report their trait anxiety. These surveys are BFNE, PRPSA, and STY. The higher the survey score, the more anxious a person is. So these survey scores serve as the labels for prediction that we are going to do later. From this data collection, we got physiological and acoustic signals. We performed some basic pre-processing like noise removal and filtering on them. After that, we sampled these signals over 15-second analysis window. We chose 15 seconds because it takes some time to manifest stress within physiological or acoustic features. After this sampling, we chose these physiological and acoustic features. For physiological features, we took skin conductance level and average heart rate. For acoustic feature, we took fundamental frequency, jitter, and shimmer. These are features that have been used in previous research about stress and anxiety detection, and they have strong correlation with public speaking anxiety. After the feature extraction, we perform a visual inspection. The left figure shows the heart rate of a participant. The x-axis shows the entire presentation time for both the figures. The right figure shows the shimmer feature for the same participant. As we can see, the heart rate feature shows an oscillatory pattern, while the shimmer feature does not. Therefore, we decided to model heart rate feature using transient oscillation model, while the other features are fitted into quadratic polynomial pattern. So transient oscillation model represents the heart rate time series. Heart rate time series is fitted into this damped harmonic oscillation equation. So T is time, Y is heart rate, and the model parameters are amplitude A, decay rate tau, frequency F, phase phi, and DC bias C. This optimization is performed using nonlinear least square regression, but it requires some proper starting points. And that's why we follow this algorithm. We initialize phi with a very small number. For the initialization of F, we calculate consecutive peak and zero crossing rate from the heart rate time series. This gives a good initial point of F. If that yields F equals 0, we set F a small number and phi to pi by 2 so that we don't lose the. Then we approximate A, tau, and C by fitting the same time series into an exponential function because it's less complicated than the original one. Now we have the approximated initial starting points for all 5 parameters. We use these points to perform nonlinear least square regression. From this, we obtain the transient oscillation model parameters A, tau, F, phi, C, 5 parameters per participant. These figures show the transient oscillation model fitting for 2 different participants. The left one shows that this participant's heart rate is faster than the right one, and it also has lower frequency. On the other hand, the right figure shows that the decay is slower and it has more oscillatory patterns. It has higher frequency. Therefore, we can hypothesize that higher tau means faster dampening, which refers to low trait anxiety, while higher frequency or higher A or C refers to high trait anxiety. Next, we move on to quadratic polynomial model. All other features like skin conductance level, F naught, jitter, and shimmer are fitted into this. We follow this equation where B is the DC bias, T naught is the point where minima or maxima occurs, and A refers to the width of the polynomial. The higher the value of A, the narrower the polynomial is. And to fit this model, we used least square regression. So these 2 figures show the quadratic polynomial model fit into a skin conductance level of a participant and shimmer of another participant. The left figure shows that it follows the habituation pattern as we mentioned earlier. On the other hand, the right figure shows the sensitization pattern. Therefore, we can say positive values of A refers to habituation and negative values of A refers to sensitization. Also, higher A and B would mean higher fluctuation, so it refers to high trait anxiety, and lower T naught, which refers faster maximum reaching, refers to high trait anxiety. This indicates that there are some association with model parameters and trait anxiety. In order to evaluate that, we perform two tasks. The first one is to determine the Pearson's correlation coefficient between these model parameters and trait anxiety scores from the self-reports. Next, we try to estimate trait anxiety from these trajectory parameters. We perform a linear regression to predict the trait scores using these model parameters from the features. To do that, we perform a tenfold cross-validation. For evaluation metric, we used Spearman's correlation coefficient between predicted and actual trait scores. The higher the correlation, the better the performance of the classifier is. To compare it with a baseline model, we used a baseline model where mean values of the same biobehavioral indices were used as features. So let's discuss the result of relation between individual trajectory and trait anxiety. So first, we talk about the transient oscillation model. As we have discussed earlier, the transient oscillation model's parameter has association with trait anxiety. Higher A and C refers to high trait anxiety, while lower phi refers to high trait anxiety. The figure shows the Pearson's correlation between these parameters and trait scores. As we can see, the heart rate C parameter and BFNE has significantly positive correlation. The same thing happened with A and STAI. On the other hand, phi shows significantly negative correlation with PRPSF. If we look at the quadratic polynomial model, we have said that higher A, B, and lower T naught means high trait anxiety. From the figure, we can see skin conductance levels A and F naught's B parameter shows significantly positive correlation with BFNE, while jitter's T naught parameters show negative correlation. So it matches with our hypothesis. Next, we describe the result of our prediction experiment. These figures show the Spearman's correlation between predicted and actual BFNE score. We use different combination of features using only heart rates, using physiological features like heart rate and skin conductance level, acoustic features, and all the features. As we can see, our proposed model performs significantly better than the baseline model. It has higher Spearman's correlation than the baseline model for all the modalities. We see similar results in the figure on the right, where it shows the Spearman's correlation between predicted and actual SDI score. Therefore, we can say physiological features, specifically heart rate, shows promising result for predicting anxiety from the trajectory model. On the other hand, acoustic features are performing a little worse than the physiological features. This might be the reason from the individual variability. To conclude, our model is highly interpretable as well as predictive of trait. And this model is able to capture the theoretically grounded time trajectories. In future, we are planning to use third-party annotations for in-the-moment anxiety detection. We would like to include additional modalities like facial expression, EG, and we are planning to use more sophisticated data-driven model. So that would be all. Thank you for listening to my presentation.